Hi everyone. In this part, I will introduce our project and explain problem 1, which is the open loop dynamic simulation of the 2 degrees of freedom planar robotic manipulator. Here you can see the general aim of the project. Basically, we model and simulate a two-link robotic arm in MATLAB and Simulink. In the whole project, we study different control cases, but my part focuses on the first step, observing the robot's motion without any controller. This slide shows the system we are working on. The robot has two revolute joints, so its motion is described by theta 1 and theta 2. At the end of the robot, we observe the end effector position as xe and ye. So in this project, we look at the robot both in joint space and Cartesian space. In problem 1, we apply constant torque inputs to the two joints. Since this is an open loop simulation, there is no feedback or correction. The robot simply moves according to the applied torques, gravity, and its own dynamics. Here you can also see the assigned parameters and initial conditions used in the simulation. Um, this is the main dynamic equation of the robot. It includes the inertia matrix, the velocity-related terms, and the gravity vector. In Simulink, we use this equation to calculate the joint accelerations. So this model is the core part of our simulation because it tells us how the robot reacts to the torque inputs. After calculating the joint motion, we need to find the position of the end effector. For that, we use forward kinematics. These equations convert theta 1 and theta 2 into xe and ye. In other words, they help us see where the robot tip is during the motion. At the beginning, both joint angles are 0, so the robot starts in a horizontal position. Because of that, the initial x position is simply total length of the two links, and the initial y position is 0. This gives us the starting point of the end effector before the simulation begins. Here we show at the right hand side, we show the first acceleration calculation. Since the initial velocities are 0, the velocity related part becomes 0 at the start, so the first acceleration depends on the torque input, gravity, and inertia. Um, this is a quick check to verify that the robot dynamics block gives a reasonable initial result. And this slide shows the Jacobian relations. The Jacobian is used to convert joint velocities into Cartesian velocities. So after we calculate the theta dot and theta double dot, we can also obtain x dot, y dot, and the Cartesian acceleration. It's also important for the next problems, especially velocity and force control. Here you can see the short numerical summary of problem 1. These values define the starting condition of the simulation, and they confirm the initial position, the dynamic matrices, and the first joint accelerations. This block calculates the joint accelerations using the nonlinear dynamic equation. Then the acceleration is integrated to obtain joint velocity and joint positions. So this block is the part that actually produces the robot's motion in the open loop model. This is the Simulink structure for problem 1. And the torque input goes into the dynamics block. Then we obtain acceleration, velocity, and position. After that, forward kinematics and Jacobian blocks are used to calculate the Cartesian outputs. With this structure, we get all required outputs for the first problem. Finally, these graphs show the open loop response of the robots. Since there is no controller here, the robot is not trying to follow a reference. It only moves naturally under the constant torque inputs. These results help us understand the basic dynamic behavior of the manipulator before adding controllers in the next parts. And here we can see the joint angle responses. theta 1 and theta 2 during the open loop simulation. These graphs show how each joint moves when constant torques are applied. Since there is no feedback controller in this part, um, the joints are not tracking a desired reference. They only respond naturally to the applied torques, gravity, and nonlinear dynamics of the robot. So these results complete problem 1 by showing the motion in joint space. Thank you.
Hello everyone, I will present problem 2. Our goal here is position control. This slide shows our 5 control steps. We use inverse kinematics and PD controller to find the necessary motor torques. Here is our MATLAB code for the position controller. It calculates the robot's dynamic matrices instantly. This cancels the nonlinear forces, so the robot moves like a stable system. For problem 2a, our constant targets are 0.38 and 0.41 meters. The robot starts from a different position, so there is an initial error. We use inverse kinematics to turn these x and y targets into reference joint angles. These are tracking results. The blue line is the robot and the yellow line is the target. As you can see, the robot reached the target very smoothly in just 1 second. And this slide simply shows our Simulink block diagram for the constant position tracking. You can see the constants. Now we move to problem 2b. Here our targets are sinusoidal. They change continuously with time. This makes tracking physically much harder. These graphs show our tracking performance. The blue line follows the moving yellow reference very successfully. There is a very small delay, but the system is very stable. It's okay. It's for x-axis and it's for y-axis. Finally, this is our Simulink diagram for problem 2b with the sine wave inputs. Our controller handles the moving the target perfectly. Now my teammates will explain problem 3. Thank you.
So now I will talk about the problem 3. So our goal of the task is to move the end effector of the robot arm at a constant velocity in the Cartesian space given x ref and y ref. So our angle is given here and our equations to calculate the positions is here. Our, as you can see in the right sides, our parameter, you can see our parameters and calculations. So desired Cartesian velocity is here and Jacobian relations, the formulations are here as you can see. So the desired Cartesian velocity is converted into joint velocity reference by using the inverse Jacobian. So this block allows the manipulator to follow the desired end effector velocity. And in block diagram, I will talk about the operation of block diagrams. In inverse velocity kinematics converts the desired Cartesian velocity into the tangent joint angles that the motors need to reach. And controller DOOB eliminates external disturbances such as gravity and inertia, providing the required torque to the motors. And forward kinematics converts to actual achieved joint angles back into Cartesian velocities, allowing us to verify if we are tracking the references correctly. So let's talk about the graphs. In overall performance, the system successfully tracks the given reference velocities for the most of the parts, as you can see. However, in some parts of the graph, there are spikes, as you can see. The sudden, sharp drops we observe are caused by kinematic singularity. As the robot approaches its physical workspace limits, the determinant of the Jacobian matrix approaches zero, creating a momentary event for infinite velocity torque, which shakes the system. And despite this, the disturbance observer structure we implemented successfully absorbs these shocks within milliseconds, as you can see right here. It is for a moment in milliseconds, and settles the robot back to the reference velocity.
Now I will present problem 4, force control. In this project, we make robots interact with an environment to apply a specific force, similar to an industrial robot pressing against a surface. To achieve this, we modeled the environment as a spring damper system. This surface has a stiffness defined by the spring constant and the damping effect. The constant force is generated only when the robot touches or penetrates this boundary. Now let's look our control strategy. Our force references are -7 newtons in the x direction and 2 newtons in the y direction. The goal is to make the actual contact force match these references. We do this by calculating the force error, the distance between the reference force and the measured force, and then applying a correction. The core of this is the force control MATLAB function block. This block calculates the required force command using proportional feedback. However, we cannot send Cartesian force directly to the motors. Our motors work in joint space, but our force goal is Cartesian space, and this is the Jacobian transpose is essential. Think of it as a mathematical bridge. We use it to convert our desired Cartesian force into the exact motor torque needed at each joint. We also include gravity compression to ensure the robot holds its position while pushing. On this slide, you can see our simulation results. The graphs compare the reference force with the actual measured force. As you can see, the actual force successfully tracks our references, and this provides that our controller is effective at regulating constant force. And in summary, problem 4 demonstrates that we can successfully control the interaction force of our robots. This concludes the force control section, and thank you for listening.